Hi, everybody. I'm so delighted to welcome you into the new building. This is our third VADA Talks, and at the other two, we were prophesying the existence of this building, and now we're sitting in it. So, and we really see it as a community space, so I'm very, very happy to invite you all in here because I want you to know what's going on at our high school and what the great opportunities our students have, especially in this realm of cultivating creative students, artists, and that's the building that you're in here. This is the design lab, usually. We've turned it into a lecture hall tonight, but you saw all the computer stations out there. The analog side is over there, and I hope you've just had a chance to walk around the building and just enjoy it and see the different technologies and equipment and the creations of the students that are being made in this space, and I hope you're inspired and encouraged by all of that. Just a quick word about what VADA is. Sometimes we describe it as like a school within a school at Santa Barbara High School, but it's not like there's boundaries or fences. Our students are a part of the student body here in the comprehensive high school, but it's just that they're tuning and dialing obviously their art education. And when I'm talking about art, I'm talking about design, digital, and analog, the two sides of this building. And then also their academics about half their school day. So VADA English, VADA History, and VADA Science are all academic classes like you would take in a normal high school, but integrated with art and design projects as ways to show your learning. If I'm a creative person, I want the option to show my learning, not just by writing, not instead of writing, in addition to writing, but in addition to that, show it with my visuals and my creativity and that kind of work I would make in a studio like this. So that's what we're doing here. It's very exciting. This is the equivalent of the stadium for athletes, or the engineering lab if you're in another program. And so I'm just so happy to just have this here for our students. And we talk a lot about the VADA family. A huge part, you can imagine if students are spending half their school day together every day for 4 years, there's quite a community and quite a sense of family that gathers around the work that we do in this building. And so we talk about the VADA family, and I just want to tell you that I think of you as an extension of the VADA family by being here tonight. I want you to go and tell your neighbors and nephews and cousins and people about this program because we want kids to come here if this is the place that would serve and inspire them as they go through high school. Even if they don't go on to be an art major, maybe 10 or 15% of our students go on to that specific of a study. They go on to great art schools, but our kids go into all kinds of different areas. And so it's just, do you want to be creative and solve problems in this kind of a way? Because the skills that students learn in here, despite whether they go on to sell paintings for a living, are applicable to any other domain that they might work in. So, okay, I'm going on. I'm preaching about VADA, and we want to be here for okay. So I think I better get off the stage. I want to invite Sylvia up to the stage to introduce our guests, and thanks again so much for coming tonight. Oh, one important thing. Part of the VADA Talks is the talk, not just up here, but the talk that happens afterward, the community dialogue, this forum that is part of the vision of VADA Talks. And so I hope you'll plan to stay with us and spill out onto the patio and talk to other friends and make some new friends here. And also, one of the best things that you're going to get to have happen tonight is to talk to one of our students. You'll see them with a yellow lanyard, and every time we have a program like this, people come up to me, oh my gosh, your student's so articulate and inspiring. I really would encourage you to talk to one of the students that you see just to hear them tell you about what VADA is like for them. There's even some VADA alum in the crowd tonight, which is really exciting. So, okay, Sylvia, before I talk too much longer. Thank you.
There we go. Hi, everyone. Thank you so much for being here. My name is Silvia Perea. I am an architect and the curator of the Architecture and Design Collection at the Art, Design, and Architecture Museum at UC Santa Barbara. It is more than my pleasure. It's really an honor to introduce our speakers tonight and moderate a conversation with them. I don't know very well what the leadership of VADA was thinking by bringing me here, but I couldn't let go of the opportunity of talking about the macro and the micro scales. So thank you so much for the opportunity. I'd like to take a moment before we jump into the introductions of the introductions, you know how this goes, to acknowledge the fact that this event is taking place in unceded lands. So in that regard, I want to pay my respects to the Chumash peoples, their elders past, present, and future generations. Thank you. And now, during this event tonight, we are going to listen to our speakers, astrophotographer Jeffrey Lovelace and scientist and engineer Erik Lucero. And their work explores many different scales. Actually, they explore the polar scales of scale. On the one hand, the vast distances and almost incomprehensible distances of the cosmos, and on the other, the minuscule and very almost abstract terrain of the quantum world. These are domains where conventions of human perception, our sense of scale, size, distance, time, and even reality become kind of fuzzy and fall apart. At these scales, our sense of reality as we know it actually is no longer a frame of reference. Our anthropocentric view, that is what we see and what we are able to measure, actually does not fit in, right? But in spite of these physical remoteness and minuteness of these realms, they are not detached from us. They are actually fundamental to who we are. When we contemplate the vast distances between galaxies or the very eerie space within atoms, we are reminded that our nature, human nature, is fundamental to bring them together. The fact that we can contemplate, document, and actually reflect on these realities attests to our great cognitive capacity, let alone the great things that we can do when we come together. Exploring these realms does not only lead us into the scientific world, it also opens up doors for other types of understanding. Artistic, as we will see today, but also philosophical, mythical, and even religious or spiritual. These liminal spaces where the known meets the unknown makes photography become a tool not just for documentation, but actually a tool for thinking, for imagining, and for connecting, as we will see today. So the presentations of our speakers will bring us into that space. Before we get into that, we are going to play a movie that I'm sure most of you know. It's called Powers of 10. It was put together in 1977 by the famous designers Ray and Charles Eames. And we will see that this is a visual journey through the relative scale of things in the universe, as the camera expands in powers of 10 outward of the Earth until the full cosmos is in view, and then zooms inward to the atomic level, down to quarks. It is a good way to put us kind of in the mood or gain us the perspective to embrace what is coming up next. Maestro, please play the movie. Thank you.
The picnic near the lakeside in Chicago is the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is a kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds. The day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. 10 to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way Galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan, 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary, containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus, so massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks at intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Well, that was mind-stretching, and a good reminder on our need to gain perspective over things when we get too entangled on our daily things, right? It is my honor to introduce our first speaker today, astrophotographer Jeffrey Lovelace, who also goes by J.K. Lovelace, or Jeff, if I may. He's been an astrophotographer and outdoor photographer for the last 35 years. His work has received all the prizes and recognitions that you can imagine. Among them are the Royal Museum Astronomy Photographer of the Year in 2021, and he was also selected as the best photographer in Your Best Shot in Flickr's in 2020. Currently, Jeff serves at the advisory board of UCLA Galactic Center Group, which is amazing. Who wouldn't like to be in a galactic group? He is actually contributing to this group, which is led by Nobel Prize Andrea Ghez, and they are studying the supermassive black hole at the center of our Milky Way Galaxy. Wow. If this weren't enough, Jeff operates from here, from Santa Barbara, super cooled down telescopes that are housed within observatories, not only in California, Sierra Nevada, but also in Los Andes, in Chile, and in Australia. His body of work is just amazing, as you're going to see, and there is currently an exhibition in the Slice of Light Gallery in Santa Barbara. I would totally recommend anyone here to go and see it if you haven't checked it out yet. If you're lucky, you will see Jeff there, and we'll give you a tour if you're even luckier, and that would be a memorable experience, I'm sure. So thank you, Jeff, for being here. Please take it away and give him a round of applause. Thank you.
Thank you. That's me. All right, let's see. All right, here we go. So the theme of tonight is photographing the unseen. But more importantly, beyond light. So photography is the practice of capturing light. So if you go beyond light, there's really nothing to photograph. So that's the end of my presentation. Thank you all very much. So I'm going to focus on an interesting aspect of photography that does go beyond light. So photography captures light or light over. Any guesses? Time. This is kind of the unexplored aspect of photography. Every photograph has a length of time, a shutter speed, a period of time that it captures, which is part of the magic of photography. You get to freeze a moment. So let's first talk about human vision. Human vision basically refreshes itself about 30 times a second. So every 30th of a second or 60th of a second. It kind of varies. It's a complicated system. the eye and the mind refresh themselves. And the light that was gathered before has been sent to the brain, and now it's gathering new light, turning it into electronic impulses, sending that to the brain to be interpreted, etc. In camera exposure times, in normal photography, using your iPhone or a DSLR camera, the typical exposure times are 1/30th of a second and shorter, sometimes up to 1/500th of a second. That's pretty typical, and it's pretty consistent with our experience of normal reality. If you want to warp time a little bit, go with a super fast exposure time, like 1/2000th of a second, and you can see things that are unseen. You can see every little feather in a hummingbird's wings as it's flapping away, which to the naked eye we can't see because at 30 cycles a second, it's just a blur. But I'm going to go the other way with this and talk about longer exposure times. But first, one of the things I do basically three things. I do landscape photography, which does not mean that I go take pictures of people's landscapes at their home. I take pictures of the greater landscape. And these are some of my images that were all shot within that sort of normal time frame that we're familiar with. So they're kind of familiar-looking images. Another kind of photography that I do is night landscape, or nightscapes as they're called. And this is where we start getting into longer exposures. The picture on your far left is about 1/5 of a second. And so at that speed, the people on the boards are moving a little bit. They're a little bit blurred, so it's not as sharp as what we would see. And then as you move along, each image is over a slightly longer period of time. Up in this corner, these are shot at about 1/30th of a second. And at 1/30th of a second, at a very high ISO, if you're a photographer, with the camera lens wide open, it's dark enough that I can't see my hand in front of my face. So I'm capturing light, basically, that is starlight and any other ambient light, which in both cases is a little bit of light pollution from nearby cities. And then you go a little farther with it, and way off to the right is a series of 30-second exposures that are basically stacked on top of each other. And in effect, they're capturing about 20, 25 minutes of time. During that time, the stars are moving. As the Earth rotates, the stars are moving towards setting, in this case, towards the western horizon. And as they move, by stacking all these images together, you can see their trails. So those are star trails. And I've processed them in such a way that they look like meteors falling. There's a whole story behind the theme of that photograph that I won't go into to save time tonight. This is an interesting and telling photograph. I'm sure many people here know where this is. This is Yosemite Valley, and it's shot from Glacier Point. And it was a good year. There was a lot of water. You've got Yosemite Falls on one side, and you've got Vernal and Nevada Falls on the other. And you've got the lights from the valley. This is a mosaic style panorama with multiple rows. And each frame is, again, about 30 seconds. But the whole thing took, a good 20 minutes to shoot. But I love the fact that this is where people go to get out of the city lights. So it has the title Artificial Darkness. But there are a couple of things in this image that I think are particularly key. In the sky, well, first of all, up in this corner up here, you can see the Big Dipper. Although in this, the way it's projecting, it's a little bit hard to see. Pardon me while I turn away from you. But it's right here. So there's the Big Dipper. And then there's this cloud here. It looks like a cloud, but it's not a cloud. And I'm sure many people here know what that is, but I'm curious how many people here do not know what that cloudy structure is. Okay. And this is great because we will be talking a lot about that. There's also a bright object up in the center up there. We'll talk about that later because that's a lot of fun. So, what that cloudy structure is, it's the Milky Way, so-called because when you get away from city lights, you look up, there's this milky cloud that spans the sky in a straight line. And it's made up of stars. We're part of the Milky Way. The Milky Way is our home galaxy. They talked about it a bit in The Power of 10. This is like we're in a neighborhood of this particular city, is a way to look at it. The Milky Way has about 300 billion stars. And one of my favorite trivia questions to ask people is, what's the nearest star to Earth? And it's kind of a trick question. The answer is the sun. The sun is a fairly normal star, a little smaller than average, but very stable, very friendly. Yeah, thank goodness. Well, if it wasn't, we wouldn't be here. That's the key thing. The Milky Way Galaxy is about 100,000 light years across. So it takes light about 100,000 years to travel from one side of the galaxy to the other, as a light year is how far light travels in a year, which happens to be, what is that, I have it up there, 5.88 trillion miles per hour. I forgot to put that in. Also, as Sylvia mentioned, I work with the group at UCLA that studies the supermassive black hole at the center of the galaxy. As galaxies go, it's a very nice, not particularly special, barred spiral. And we happen to be in an area of it that is kind of in a not particularly fashionable neighborhood, as they would say, in that in some areas there are many, many more stars more closely packed and a lot more going on. We have a lot of distance between us and other stars here, which kind of makes it not as compelling of a night sky as it might be in some other parts of the galaxy. But here's an interesting thing. What would it look like to be inside of that galaxy? And this is an artist's rendition from the ESO, European Southern Observatory. So that is what it would look like. And you see a lot of dark blotches. These dark blotches are basically dust clouds, and they can block our view of other parts of the galaxy, but they're also very interesting because that's where stars are born. It's in these areas of dense dust and gas that you have gravitational collapse that pulls more and more material together that eventually creates new stars. Now, think about that middle picture there. And then look at these night sky images. there is the Milky Way. And you see that, yes, it is the same structure that we can see. And you can see this at night with your bare eye, with your naked eye, with your unaided eye. It looks to the eye a little bit like the image on the right, just more of sort of a bluish cloud that goes across. But in the camera has much better low light sensitivity, especially when you have the shutter open for 30 seconds. So over 30 seconds, it's able to pick up colors that we can't see in low light with our eyes our eyes are really attuned to daylight. They're not very efficient in the dark. And so what you see is a lot of bright red areas, and you can also see the dust clouds, the dust lanes, but the bright red areas are nebulas. They're giant clouds of gas, and mostly hydrogen, but also a number of other gases like sulfur and helium and nitrogen and oxygen. It gets really interesting. And so now let's go back to our picture here and talk about the bright spot. The bright spot is the Andromeda Galaxy. So we can see, and you can see this with your naked eye if you know where to look. It just looks like a fuzzy thing, as you know, again, as long as you're away from the city lights. That image of the Milky Way, people often ask which space telescope that's from. Is that from the Hubble or whatever? And the answer is no, it's not. It's from that telescope. That's one of my telescopes. This is located in the Sierras. It's got a computer mounted on it. I'm looking the wrong way. But that's all the equipment that I've pieced together on this, including the cooled camera, which doesn't look like a camera. It's just a box with a sensor in it, et cetera, et cetera. And this is sort of a medium-sized telescope. But the key thing about this shot is that now we're getting into actual deep sky astrophotography. And one thing I want to point out, this is where time gets really stretched. The Andromeda Galaxy is about 4 million light years away. So it's taking the light 4 million years to reach us. We're seeing as it was way back in time. Here's another interesting thing to think about on this. The size of that is a little bigger than the size of the Milky Way. And considering the tilt and everything, it's roughly, the front side of it is roughly 100,000 light years closer than the back side of it, maybe 150. So the light from the back side of that is 150,000 years older than the light from the front of it. So we're not even seeing a picture of it at a particular point in time. We're seeing a picture of it over hundreds of thousands of years. So, this is some of my other deep sky astrophotography work. And this is all within our galaxy. The only thing I can shoot outside of our galaxy are other galaxies. But all of this is within our galaxy and generally within our general neighborhood of our galaxy. Because all those dust lanes and everything hide so much of it from us. So what we have on the let's start with the left, is, again, these are these red areas that I was mentioning, the nebulas. And we've got big clouds of hydrogen, which are the red, hydrogen and sulfur. And then we've got some blue areas down underneath the big cloud there, and that's oxygen. And then we've got the sandworm-looking structure that comes out, and that's that's a lot of dust. The gray and the black areas are dust, and so there's probable star formation either happening or about to happen in there. And it looks like it's going to eat that galaxy. But the galaxy is actually, hundreds of light years away, so maybe thousands. So it's not going to do that. Whereas this is probably only, I don't remember on this one exactly, but I'm thinking it's about 7,000 light years away. The one next to it is an area where a star was recently created, and by recently I mean only in the last few million years. So it's just a baby, and it's beginning to push away the nebula around it that created it. The one in the middle is very interesting, and I'm going to have to turn and point with this. This is a supernova remnant. So a supernova happens when a very large star, much larger than the Earth, than the Sun, starting about 8 times the mass of the Sun. When that reaches the end of its life, it explodes in a very spectacular way. And it violently throws out all of its gases and everything, all except for the very core of it. And in that process, new elements are being born in these shock waves. It's very exciting. And this shock wave spreads very rapidly. Next to it is this one here. This is how a star about the size of the Sun, or maybe a little bigger, will die, which is much more gently. It gets so hot in the center that the outer shell of it, the top layers just kind of get pushed away. They expand and they float off into space. These look like they're the same size, but they're not. The supernova remnant is actually about 20 times farther away. It's just one of those forced perspective things. Then, in addition to that, you've got an area in the lower area. This is another area of star formation. So you've got star birth and you've got star death. There's a lot of drama out there. It's very exciting. This is another area of star formation. This is called the elephant's trunk. And up in this, you can see this little hole where new stars are forming, and they're beginning to push away the dust cloud that created them. And then over here, we've got another supernova remnant. And I just love the patterns and shapes that are created in these violent actions. Now, this is the other thing, and this gets back to the power of 10. In all of these images, think about our solar system, our sun, all of the planets. On the scale of these images, how big would our solar system be? And the answer is they would fit quite neatly into 1 pixel. So that's the entire solar system. And then, of course, within our solar system, the Earth, you could fit 1 million Earths inside the sun. So the Earth is very tiny. Makes you feel important, doesn't it? So getting back to the art aspect of all of this. Oh, by the way, actually, let me go back. In terms of exposure time, again, like these are typically, a few thousand light years away, but because they're that far away, they're typically very dim. These typically take about anywhere from 20 to 200 hours to photograph. And it's done with these telescopes, photographing every clear night that isn't a full moon, and taking basically 10 or 15 or 20-minute exposures, one after the other, after the other, after the other. And then the next night doing the same thing on the same target. And doing that for a few weeks, or sometimes a few months, or sometimes 6 months, and then it's no longer in season. It's now aligned with the sun, so we can't shoot it, so we have to wait a few months, and then we start doing it again. So some of these I will take over the span of 2, sometimes even 3 years. So again, talk about time distortion. That's a long exposure. But, you know, we're here to also consider the artistic value of it. I was drawn to astrophotography because I saw an image when I was young and just went, whoa, that's beautiful. And so I've always wanted to do this and launched myself into it at as young an age as I could. So my work is currently on display, as Sylvia mentioned, at the Slice of Light Gallery, which is on Figueroa. We have Garrett Tornello here, who's the manager of the gallery. And one of the things I like to do is take some of my astrophotography out of context, remove the stars, and just show them as pieces that are free of any time reference, any other size or scale reference. And so these are some examples of that. And you can see, you know, this one up here looks, you know, you've got some really nice sort of painterly color tones. And in this one, you've got some drama of a figure that's reaching up. This one's called Perseus beseeches Andromeda. Or no, I'm sorry, Andromeda beseeches Perseus. Sorry, I'm getting my mythology mixed up. The one in the middle is called Plasma Dance. Again, it's some superheated gases it's a shock wave that's passing through the universe. But if you didn't know that, it would just be a very interesting form that some people think looks like a dancer. And some people have noticed 2 different dancers in this, which I'll leave that to your imagination. And then we have a very colorful interpretation over here. So there's a lot you can do artistically with this as well that isn't a literal reporting of what's in the night sky. So let's bring this back down to Earth and our normal frame of reference, our normal reality. And I'm going to show you a video clip coming up. Last summer I was up in Yosemite and set up a camera and did a time-lapse video. It was actually a time-lapse intended to just capture single frames of meteors. But I happened to capture all sorts of other stuff that was very interesting that night. And in this, you will see all sorts of very exciting things, and I'll kind of narrate it a little bit. Garrett helped me put this together. This is the moon. The moonlight the moon's now setting. And we've got the green and magenta of what's called air glow. It's the upper atmosphere glowing. And you've got some car taillights and car headlights. And in the sky, you've got some meteors, but you've also got planes and satellites. And of course, there's the Milky Way cloud as the Earth rotates. But on this night, this was a lucky night because the aurora borealis managed to come this far south, the northern lights. And this is the North Star, and notice how as the Earth revolves, it looks like the sky is revolving around that point. And so again, it's about time. If you look at this time scale, it's very obvious how the Earth turns, how we're not stationary, how there's motion. And again, there's our friend, the Andromeda Galaxy. So that is the end of my talk.
Thank you, Jeff. That was a long exposure in the dark. Well, thank you for your presentation.
I do tend to go on.
Well, because we're on a time schedule, I need to present our next speaker, who is the lead scientist at Google Quantum AI here in Goleta, Dr. Erik Lucero. With his permission, I'm going just to call him Erik. He has been engineering quantum systems from the qubit to the campus scale. He not only conceived, but also designed, built, and currently operates Google Quantum AI in Goleta, as I said. It's kind of a hidden facility, but a lot of what's going to change the history of mankind is happening here. In this facility, actually, Erik is trying to solve otherwise unsolvable problems with quantum computers. In 2019, he was part of the Google team who proved quantum supremacy. And what's quantum supremacy? Well, they proved that a quantum computer was much faster than the Earth's most powerful supercomputer in solving a problem. Actually, it took only 200 seconds to their quantum computer to solve a problem that would have taken the Earth's most powerful supercomputer 10,000 years. So that was not only a breakthrough of the year, as they said, it was a breakthrough in history, and they're only getting better and better at it. He has 2 decades of experience in quantum architectures. He has worked not only at Google operating qubits, but also in a lot of the fanciest labs around the country, including some competitors of Google. So he has all the insights. Alongside his very successful career as a scientist, he's put together a portfolio documenting the evolution of the quantum computers and the quantum processors. So he's also an artist. His photographs have been published and reproduced in many media and in many formats. And actually, there is a photo of him in the corridor that he brought today alongside one of the photos of Jeff as well. And on top of all of these things, in 2018, he funded alongside Forrest Stearns, who's an artist and he's a past speaker at VADA too, the Quantum AI Artists in Residence in their facility in Goleta with 3 objectives, basically to learn to speak the language of nature, to reconceive how a scientific lab should look like, and also to inspire new teams and future generations on further developing quantum computing. Please join me in welcoming Dr. Erik Lucero. Thank you.
Thank you for that really lovely introduction. I wrote some notes from this morning that I wanted to share. So earlier today, we had the pleasure of speaking with the students, and it was a really lovely session. The 3 of us here, and the students came. And we got a chance to talk to them afterwards. I heard a number of them are about to graduate, and they were kind of grappling with finding worth and their own impact and the work that they're about to do and that they're doing. And I thought that this was a really lovely space right here today that shows that this community here cares a lot about the work that these students are doing. And I see it both in what VADA is doing, bringing this art, design, and creativity to the world. And I see a lot of friendly faces and folks here in the audience that I've had the pleasure of working with and bringing creative things to life. So thank you all for being here and engaging in these things for the community. Thanks. So with that, I wanted to start by thinking about what it was like when I was that age in high school. This is me studying math and also playing music. So I was working my way through college, and one of those gigs was playing records. And I also had a camera strapped to my hip throughout my college career. And I did have a high school photo lab as well. But it was really in college that I had access to one of the nation's largest wet labs. And as soon as I left that space, my art teacher told me, you probably ought to pick up a digital camera. And I'm glad I did. And I've had the pleasure of now walking around with a digital camera as I've pursued a degree in electrical engineering, applied physics, and a PhD here in Santa Barbara. And I've had the pleasure of now running and creating this campus here in Santa Barbara and founding this artist in residence program, which I think is an important part about this concept, what I would say is the human perspective, where we talk a lot about these, the artist perspective or the scientist perspective, and I really think that it's about weaving these things together. And so it's not just saying that, but it's actually trying to do that. And so I hope with some of these images and some of the work I get to talk to you about will show you how we're trying to do that. I'd like to shout out to a number of folks that I see in the audience, and one in particular is a co-founder, friend of mine, Forrest Stearns, where we've created this artist in residence program. And in this space here, I've got a couple of great friends and architects in the audience as well that I can look at and see that have helped us design these spaces. So thank you, thank you. And in that, it was fun to see when we put up some of these pieces, initially some of the reaction of the scientists that I work with, my colleagues and peers were like, what are we doing? And then as we started to move in these quantum computers into that space, as you look at it today, it's completely transformed. And you can't even see the boundary between what is an architecture or what is science. I have another artist in residence with the program that has been documenting this work for over a decade. He joins us here as well. And this is a really lovely opportunity to show when we were first putting the first piece of art on a quantum computer. It's how you headhunt an artist from a space team. You say, let's figure out how to put art on a quantum computer, which is a nice connection to the piece that we saw earlier up in Yosemite. These images are not mine, but they are a great showing of the space as we were beginning to inhabit it. And then it's really fun and lovely to unveil what is actually going on in this sculpture here. And I say it's a sculpture because this is touched by human hands. Many hundreds of hours are put to building that machine that you see there. And it's composed of very particular metals. And a lot of thought and work is put into each one of these systems. I'll talk a little bit more about them, but I thought I would give a quick primer, a couple of slides about what quantum computing is. So you can take a little bit with you, and we'll also look at some photos, I promise. But if you want, I can talk about quantum computing all night. I think the first thing to note is that quantum is the language of nature, and quantum computers speak quantum mechanics. Now, I don't know the last time that you all picked up an abacus, but you probably carry these supercomputers in your pocket like everybody else. And those supercomputers are basically in the same computing class as an abacus. They're governed by Boolean logic, and we've done a lot of really amazing things with them. They're very versatile. However, they are a coarse approximation to nature. On the other side is a quantum computer, which is governed by the laws of quantum mechanics. And with that, we can actually provably solve problems exponentially faster on a quantum computer. Now, don't worry, you're still going to have your classical computers as well. They will live symbiotically together, but there will be things that we can do on a quantum computer that would otherwise have been impossible for humanity. And so what is a quantum computer based about? Well, if you look over here, there's a couple of things that you could do. Some of the original proposals for a quantum computer were to take what Mother Nature provides and choose an electron. And an electron, we're familiar with, has kind of a property called charge. It also has a property called spin, which can be spin up or spin down. And those two quantum mechanical states you can encode as a qubit. Where I work, we actually choose to basically fabricate atoms, these so-called artificial atoms that we make out of superconducting circuits. And this is an image of one of those. It's a couple hundred microns on a side, a little bit larger than a human hair. And that X there is what's forming essentially a resonator, all right? And that resonator is this qubit. And here's an image, as I promised, of some quantum computers. So this is a processor that you can see here, really lovely diffraction. And I'll speak a bit about just the light there, which is really fun to play with. Most of these images that people show of devices are typically orthogonal or perpendicular to the axis in a flood of light, and they look really flat. And then you start to put some angles and some dynamism into those images, and you get some really great diffraction patterns and these rainbow patterns that happen across that. Some of these lines that you see in the line work here are a couple microns in diameter, so about 10 microns thickness. And everything that's basically black in this image is aluminum. In this case, we were building these on top of sapphire, which is kind of like a dirty aluminum, or aluminum oxide, if you like. All right, last one on quantum computing and control. This is the metaphor I want you all to think about. I love music. I loved playing music, and I continue to have a music practice, so I like to make the metaphor here to think about how we control qubits. So if you were to look at a quantum circuit on a piece of paper written out, it would look a lot like sheet music. And it turns out that if you pluck a guitar string, it has a resonant tone. It's a key. It's playing some sound waves, if you will. And our quantum gates are a bit like playing that note. And if we were all in a band together here, called the Quantum Mechanics, we'd be up on stage, right? We'd have a whole bunch of synthesizers with us, and we'd be kicking out some arbitrary waveforms. And that arbitrary waveform generator is what's making these electrical waves that when they're on resonance with the qubits, these qubits dance, all right? And as Sylvia had mentioned, that we had this really wonderful, I'd say kind of our breakout album, which was this quantum supremacy paper. She said it much more elegantly than I did. Okay, this is a fun trip down memory lane. This is a piece vintage, I think like 2007. And what was really, I was remembering and I was recalling as a graduate student, I'd go to see my peers and myself. We'd go to give scientific talks at scientific conferences, and it'd all be very good science speak. It was great. And what I remember was, again, those really flat, awful images. At best, somebody might do some false coloring to match the data in their plots. And of course, when you're talking to your peers, you're talking about the data, and everybody's very excited. And I was like, man, I know we do really beautiful things. What if we actually, start to look at these in a little bit different way? And I remember looking back at this image, how it was, and it looked through my macro lens as I began to rotate that device and get a little bit more of an angle to it, that I think you now want to trace through this image. It kind of guides you through the image. You don't know what you're looking at. Maybe some of you do. But it's really lovely geometry, shapes, and movement. There's really great light play. There's these highlights that kind of draw your attention to points. And in fact, the points that you're drawing your attention to are some of the most relevant points of this design. There's a qubit, and it's connected to a resonator. And there are these really beautiful jumpers that are coming across. Those are air bridges of aluminum metal that cuts over this connection. And we've removed the kind of silicon and the air below that, so it's just floating across that. And you can almost see in this image as well, there's almost some shadow play because of the perspective that you have, and you have some translucency. There's actually a grid, there's a pattern of aluminum with little squares cut all the way through it, but you can almost see through it because of the angle that I took this image at. This was created aluminum, again, on sapphire. These images are, again, some more of some fun quantum processors. The image here, to everybody's right, is you can see the kind of logical progression of the first one, which was a single qubit coupled to a resonator. In this case, we've got two qubits that are coupled through a resonator. And this was an experiment where we showed, we basically proved Einstein wrong. He'd been working so hard to say they were these hidden variables, and quantum mechanics is all a joke. And in this experiment here, we showed what was called the Bell violation, which was a lovely experiment that was a big deal in the science community. But it's also a really beautiful picture. This experiment here was done. What I love about it is that you have this kind of these different colors that have now come into play, and those are because of a silicon dioxide. So silicon, and you're adding a little bit of oxygen to it, gives you these different thicknesses, and depending on how much silicon we would grow, the silicon dioxide we'd grow, we'd get these different color patterns. And you can see in this image, there's a little bit of that purple to it across the whole device, and then it has these cutouts where it almost looks like there's like a cyan and a pink coming in, and those are just very different thicknesses of that dioxide, which is really beautiful. That was this Science journal rated that actually a breakthrough of the year in 2010, which was a really cool science experiment as well. We put a mechanical resonator in a superposition. So we had shown that we could do that with electromagnetic, like with photons, but for the first time we did it with phonons, which are quantum mechanical resonator. This is, I think, kind of like an intimate moment. What I remember in the lab is so much of the time that I spend with these systems. And this is in this moment where, I don't know, I guess maybe I'm also a big film noir nerd, so a lot of my lighting is kind of moody, right? And I like having these kind of, somewhat dark settings, but this has, I think, at least 3 lights where I really wanted to work on warming this system. I think they are very beautiful, and I think that with the kind of gold and copper at play, there's just a lot of really warm metals that when you light it right, you get some really great moodiness to it. And this is this moment right before this quantum computing system is about to receive a processor. And so the wiring is kind of loose, and there's kind of this next setup that we're about to bring the device in. There's also a lot of really beautiful kind of innards that are on display, and some of the refrigeration. Are folks familiar with the Kelvin scale? Yeah, sort of? Okay. We're all enjoying a really balmy 300 Kelvin in here. It feels nice, right? If you were to, when this is operating, if you were to touch that top plate there, that gets down to 4 Kelvin. So let's kind of run our scale here. Water freezes at 273. Nitrogen becomes a liquid at 77. Helium gas becomes a liquid at 4 Kelvin. That's like hanging out in some of Jeff's pictures between galaxies. It's really cold. It's really cold. If you pump on helium, helium-4, you'll get down to 1 Kelvin. That's kind of the next plate down. And then the next 2 plates down, you get orders of magnitude colder. And so the very base plate there, we call that the mixing plate, gets down to 10 millikelvin. So these are some of the coldest places in the universe here in Galita. This is an image of a device that we created, and what I like here is you get to see kind of this on the wafer still, and there's 9 quantum elements in this. Maybe you can count them. The little kind of peppermint twists, those little candy-looking things. Those are some of them, and then the squares on the edges with the kind of really beautiful orange running to those. That's some of the, again, in this case it was amorphous silicon. It's a pretty word for silicon dioxide as well. I worked many years, though, to get that amorphous silicon to look like that, so I was very proud of it. And then we put it we basically package it up. And this is in its package where you've got these really fun, like, these are huge, these copper traces there that are coming in or poking in. That's like from a coaxial cable. This is like the brute force experiments that we were doing back then. You cut up an SMA cable, which is like the coax cable that brings the internet to your house. And we brought those in on the edges. And then these little wire bonds that you see, those are aluminum wire bonds that connect from that little SMA cable onto the chip. And the pattern that you see here in the light also is this rainbow pattern, right? That diffraction that is actually due to all of these little holes that have been cut in the ground plane. So the aluminum is patterned with a whole bunch of little holes across that ground plane, and you get this really lovely play when you have multiple, hits of light versus if you just look at kind of flat, but still interesting. But wow, so much more dynamic with a little bit more light. This was an image I worked on to describe an invention I had made to help people kind of understand and sort of pedagogically. So there are qubits here down the middle. You can see that I've labeled them on this chip. And there's a kind of a starry night pattern, very regular pattern. And that starry night pattern is kind of the Oreo filling. That Oreo filling is indium, which is a soft metal. And that soft metal is also a superconductor, but it's also compliant. And we're able to flip this chip on top of the other and create this completed device. It's a so-called hybridized device. And those indium bumps, not only are they compliant and kind of soft, but they also superconduct. So they allow us to make a really great electrical connection and a really great mechanical connection. This was the first device processor that we created that really took use of that allowed us to make basically a bilayer, like 2 lines of qubits in a row. This is the wafer that you see as we were fabricating it on the left and right. And then as we cut it up, this is the piece with maybe a shout out to kind of a Johnny Ive style Apple photo or something, but I was really inspired at that time of that kind of style. And this is its companionship with the Oreo filling here, and you're getting some really lovely lights from those peppermint patties again, those little squigglies. Those are resonators, and they just have a bit of a diffraction pattern with the light. And then we hybridized devices. This is now that chip flipped on top of it. We had and we continue to have a lot of biomimicry in the lab that inspires a lot of our work. I think we all have a lot to learn from the bristlecone pine. This is the sycamore device that we used to create this quantum supremacy experiment. And you can really see this glowing. This was feels like an artifact from the future, some jewel piece that has arrived here on Earth. And this was the quantum computing system, the full quantum computer, where that sycamore device got mounted and showed this beyond classical experiment. I remember even this image, a couple nights of really sitting with this full system open and playing with light, really setting things up, maybe even using some of the paper that I saw Daniel doing, cutting this up, keeping things really dark in the lab, and getting it really set to have a really great space to get some fun photos. This is what it looks like when you're laying on your back, wiring up a quantum computer. And a lot of love, a lot of hands have moved. You can kind of see the swirling that has to happen in order for there to be a copper can that we paint with like a NASA black to actually absorb all of the infrared radiation. We want a really quiet, cold place for our qubits to reside, almost as if we were going to put this into Chaco Canyon, into a kiva. What I love about this is seeing human civilization, thousands of years, building structures that look like what we are building today in a quantum computer. This is a fun video, again, thanks to Cinedata and James Darling, who created this really lovely time lapse of putting one of our systems together. These are all infrared radiation shields that go on, and then we, basically looks like you're going to shoot it to space, but our launch is just stay inside of the lab. We pump them out, vacuum them out, and then we put on a magnetic shield to block the Earth's magnetic field, and of course wrap it in the Bob Ross blanket of love. This is an image of one of the scientists, the engineers on my team, that is, again, working very intimately with this machine, wiring all this up to make sure that every one of those wires is going to the right place. You can see a bit of where her perspective is in this shot, and a lot of control wires. This is a 105 qubit device. This is the Willow device, and yeah, there's a lot of wires. This is the full Willow quantum computer all wired up. similar to what the engineer there was working on afterwards, and kind of fun to see all of the cans off, so you can see all of the wiring coming in on that. Also, it is kind of moody. I guess I've gotten a lot of this film noir stuff that I've been thinking about. This is fun too. I think this is a lovely image of, this goes a ways back about 4 qubits, and the X in the middle on this one is actually how they talked to one another. So this was a always-on coupling of these qubits, and these lines that came out allow you to do some control with them. We've evolved quite a ways from this, but it was a very big deal. This was kind of the extension of that Bell experiment, but done with 3 and 4 qubits. And you've got some great line work going on with Chaco Canyon and these kivas. And this is the generation of Sycamore processors. I just really love seeing the kind of the scale of things, and also the warmth that other metals bring. This is aluminum on silicon is the chip, but then there is this copper and aluminum around with some really warm lighting to give you these kind of laser beam patterns that are just fun. I thought it was also relevant to try to put this into perspective as well. I have another artist in residence who is Navajo. They call themselves Dene, and his name's Ravis, and we spent, about 12 to 20 days, it seems like a time dilation for sure, with him in this space, which is a very special place where he grew up. You can actually see him in the right for size comparison there. This was his home, and we got a chance to spend the time with him. He has created a piece as well for our quantum computers. He's a silversmith and makes really beautiful pieces, storytelling devices. And this is an image of Window Rock looking through that. I felt like it kind of felt like a window looking through the sycamores as well. This is just some fun spots to go, and I'll conclude here with when we spent this time, when I think about these moments beyond light. There's this time I spent looking down at Canyon de Chelly. I think this was probably about 3 hours that I watched the light move across that canyon, where the next day was kind of like in preparation to go with Ravis down into the canyon. And we walked into that canyon. This is where he called home. And he knew exactly the right time when the shadow on that rock that you see, which is called Spider Rock, would give way, and there'd be a little beam of light that lit up this hogan. And he said, just walk with me for a few more minutes. And then he said, now turn around. And that was the right time to take the picture. And to bring it back full circle to some of the stuff that Jeff was talking about, we have here a Sycamore processor, the lab space that we are doing this work in, and I've had the pleasure of photographing some of the prototype fusion reactors here on Earth, which is this idea of harnessing the power of the sun for what would be some really great clean energy. And this is a fun kind of way to bring all that together, of bringing the sun here on Earth. All right, thanks everybody.
Thank you so much, Erik. That was mind-exploding. I see a lot of people here using Google to find out more about quantum computers. Thank you so much. I'd like to start this conversation by asking you about the intersection of art and science in your work, because both of your work sits at the intersection of both fields. How do you see these two disciplines informing each other in your work?
Okay, I can start. Yeah. Okay. Well, thanks for the question. And I think a lot about the intersection of art and science. As I think about the way that a lot of all of us walk through our lives, I think having a practice of art, whether it is a formal one or informal one, I think is an important part that allows our both, if you will, the both sides of the brain to work and puzzle things out. And I think that we bring our whole selves to problems in that way. And sometimes we may over-index on one. And I think having that balance provides some of this intuition and helps build a rich way to think about not only the way you might be working on something, but how you might explain it to somebody. And I certainly believe that it helps invite curiosity and having more people ask questions about what it is that is going on.
Yeah, totally agree with that. And the curiosity part of it is really key. I mean, to me, art is very much an emotional experience. And kind of what you're alluding to, I tend to be in my head a lot. And so art is something that gets me out of that, gives me another way to experience life. And space has been something that whenever I would see an image of it when I was young, I would be like, wow. And I remember seeing images in textbooks when I was in high school and just being overwhelmed with the beauty of it. And so I've always been attracted to the beautiful side of space, but also just, this planet we live on, and, there's no end to it. And, for me, it's very much an emotional, almost revelatory kind of experience.
So here you say that, it prompts curiosity, it's an emotional experience. Do you feel like your viewers, the audience, need to have a background to fully appreciate your work, or not necessarily?
I hope not.
These are quite, both of your work are breakthroughs, right? So what are your thoughts on that? Because to fully appreciate it, do you need a specific background in each of your fields, or?
I'll go first.
Please, yeah.
I hope not. I hope that, with the ones that I showed at the end, where the context of space has been removed, especially, I hope that people can view it not knowing what it is and still appreciate just the form and color balance and all of it. In some senses, having a technical understanding of what they're looking at helps. In some senses, it actually kind of hurts, because then at that point, you can get too in your head about what you're looking at and begin to become too analytical. But I think the sweet spot is in between, where you have enough knowledge to really appreciate what you're looking at, but that emotional impact is still there.
I'm reminded of a time when my boss's 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 boss didn't know that we had an office in Santa Barbara doing quantum hardware. And so what I did was I took a bunch of these photos that you see here, and I hung them up in Mountain View. And I started to share amongst what was mostly a lot of software engineers and research scientists, and reminded them that we build hardware, and this is what it looks like. And that inviting of curiosity, I think, was, without them knowing at all what we were up to, was what gave them the door to start, tell me more. Right. And in some cases, that snowball then led them to being very excited about the work that we were doing and asking questions.
And I want to follow up on again, the curiosity part of this, which is that I love to inform people about space and about photography and about space photography. And I do appreciate that people can be struck emotionally by an image, and then it gives me the opportunity to inform them and to foster that curiosity that the image has created.
Each of your photos requires a set of conditions which are quite not normal. Can you speak a little bit about the kind of the ritual and the requirements that each of your shots entails?
All right. Wow. Again, I do sort of three different styles. The most ritualistic is really the deep space stuff. I've gotten to the point where, as we discussed, I have telescopes in various places around the world that are permanently installed there. I control them from my home office. And so basically I spend a good part of every day planning what's going to be shot that night, where, checking the weather conditions in each of the 3 spots, and looking at what quote-unquote data I've gathered on each, using which filter. I use a variety of filters. I've set up targets for how many images I need for this to be done. And so I go through this whole ritual every afternoon before I go to bed to just get everything set and running. Then theoretically it all works very well, which is kind of a rarity. And then in the morning I go through the ritual of seeing what I caught the night before. Every morning, I like to say every morning is like Christmas, because I get to see the images that came in overnight. And so every night I have to go through and go through every subframe and evaluate it and see if maybe clouds came in and kind of slightly ruined it, and so then I have to mark that as bad. There's just this whole ritual that I have to go through. And then I spend the middle part of the day researching new targets. So it's very much almost a 24-hour thing.
Wow. I don't have that same ritual. I think it's bursty for me. It's very bursty, and I find that there's moments where it grabs me and it's like, this is what I want to do, and I want to spend the time capturing this moment, or I see that something is on the horizon. It could be that there's really great light and that's the thing to go for, or it could be that there's something really important in the lab that I have a sense is about to happen. And it's like, this seems monumental. This feels like the right time to kind of push things aside and settle in with whether it's the team or whether it's with the technology. And then spending the time to get the shot. Through the night, typically, is the time that I would say evenings and nights, just it feels like maybe it's back to that film noir.
Do you need specific conditions in terms of temperature, light,
fair.
cleanliness?
Yes, for a lot of those shots with the devices, those are done typically in a clean room setting. And so I get to don, some bunny suits and gloves and wear the full, and just try to limit the amount of dust. And I love a lot of warm lights, so I have a lot of different ways to bring warmer lights to what I feel like is usually a lot of blue light in science and device photos. Yeah.
And in such controlled environments, is there room for creativity when you're taking the photo? When all those settings are so constraining, are they enablers for creativity or limitations?
I mean, I love boundary conditions like that. I think that's also a good way to have a practice of trying to do things within a really tight way or something. And through that, you have to puzzle it. You have to be, that's, I think, when a lot of creativity shines. So yeah, for sure. Especially in a bunny suit.
What about for you, Jeff? I mean, your conditions are pretty also limited in terms of this has to, things have to be in a certain way to work.
Yes, and in the deep space photography, the subject I'm photographing has to be available. It's not in line with the sun. There are all of these conditions that have to be met. But in my nightscapes photography, and also daytime photography, again, there's a lot of research that goes into it. And, for instance, I have an opportunity this weekend to go to, if I want to do this, go to Yosemite and be on Wawona Road in a particular spot. And at 4:23 in the morning, the crescent moon is going to be rising right across the point of Half Dome, and it's exactly. And this is way the other side of the tunnel. So with a very long lens, I could capture that moon at just probably about a third the size of Half Dome, and so I've planned all this out. you know, and I'm not telling. So, you know, I'm not sure that I'm actually going to take this opportunity, but yeah, but you know, it's yeah, but you know, it's this whole thing of trying to get all the conditions together, so that I can get a really great shot, like the one of the sand dunes with the crescent moon. That was planned out long in advance. So yeah, thanks.
And then there is post-production, right? There is a lot that can be enhanced and visibilized through post-production.
Yeah.
Tell us a little bit about the room for creativity in that phase.
Well, in the deep space stuff, it takes me about a good solid week sometimes to process an image. You know, I end up with hundreds and hundreds of individual frames that need to be combined and then interpreted, and then you've got a lot of, because these are very dim subjects, you've got a lot of noise that you have to figure out a way to filter out, and then, you know, towards the end you get to be creative. You can, if you want to, you can, as I did with some things, remove the stars, or you can work with the colors a little bit, and on rare occasion a lot, just for the fun of it, just to create a more pleasing experience. So it's, you know, it's a lot of work, but even with, you know, even back in the film days before Photoshop, it took a lot of time in the darkroom to get things just the way you want, with, you know, dodging and burning and you know, all these other inventions of Ansel Adams, and, you know, so that you're customizing the print versus the original image. So yeah, it's the real creativity. As Ansel Adams said, a good photograph is made, it's not shot. Something to that effect. Yeah. I mean, the creativity is really in the processing.
As you spend nights after nights and nights at the lab, have you ever experienced a moment of revelation by looking at the space, and maybe a moment that has changed the way that you photographed and that you were not expecting, of course?
I mean, I think a lot of so yes, I've definitely had those, I would say, kind of spiritual moments where it's like, wow, like this is the image, and it just, you know it's there. I don't have to wait until the morning. So it's a little bit more immediate, but I think and sometimes it's like a couple runs at it, but then I know that's going to be the shot. Yeah.
Yeah, that kind of moment happened. It happens often with me when I'm doing these, but the one with the sand dunes and the crescent moon. When I got the color of the sky just right, I just tweaked it just right, and I was like, that's it, don't touch it. You know, it was that moment of, it's perfect. It was really exciting. And that was like the most clear-cut example of that. But, you know, in another way, just working with the subject matters that I do, it's all very sort of existential, and it's just like, what's the meaning of life? You know, we're on this little tiny dust speck, traveling at a high rate of speed through, you know, through the galaxy as it rotates, and you know, what is the meaning of life? And all that you know, that kind of thing is ever present in this. So yeah.
Wow. Dealing with the macro and micro. Yes? One more?
That question, and then let's take a couple.
Okay, yeah, absolutely. Then I'm going to shift my question. Following up with your last comment, I wonder if by spending so many hours looking at the deep sky in space, And the same for you, Erik, looking at the microscale of these quantum processors. Do you have any reflections of, the mundane world when you come back to Earth, and humanity within it?
Definitely. We're in such an amazingly, mind-bogglingly rare spot. We are so lucky to inhabit this little planet, this little bubble of atmosphere that we exist in. I like to point out that if you travel the same distances from here to the Santa Barbara airport, but you go up, you can't exist anymore. There isn't enough oxygen. It's just that far away. If you travel the distance from here to Santa Maria, except you go up, you're in space. Space isn't way out there. It's right there. And we have such a fragile system here, and we all need to take care of it. But, in addition to that, what I come, having this forced broad perspective on things makes me appreciate humanity even more, because we're all we've got, and I don't take things as seriously as I used to, because I know it's all temporary, and we're only here for a short time in a vast cosmos of that operates on a whole different time scale. So it's like the time we have is precious, and the people in our lives are precious, and the structure of society that allows us to live the lives we want to live is precious. It helps me really appreciate all of that. Whew. Thank you.
Erik, any thoughts before?
That's a tough one to follow. I would say that I feel like there's a lot about the work that, I see what Jeff's done, and when I think about the work that I've done with some of these photos, and a lot of it is trying to show some of the places that we want to go and explore, or the places that we have in some ways explored ourselves, and bringing that back. And it's like the best part when you go on a trip and you get to tell somebody, what was your trip about? And you get to share that story. And having these photographs of, whether it's of quantum devices that I believe are, at the edge of a lot of the things that are happening today, and to bring that back to show people, this is coming, this is here, we've been doing this work, or I got to go and see this. So I think it's a lot about that exploration and bringing that back.
Beautiful. Let's give him a round of applause, too. We are going to open it up for questions.
Let's do a couple questions, and then we're going to exit and do a reception, and the speakers are going to be available for as many more questions as you have. Is it working? Yes, we are. It's half question, half commentary. One of the things that struck me when I was looking at those incredible supercomputers, quantum computers, was reflecting on 20th and 19th century machines that were built with beauty in mind. Wheels that had curves, and not just a brute strength whatever. And it just struck me that especially that supercomputer, your telescope, yeah, that's a little brutal, but it's a beautiful machine. And the question that I had that accompanied that thought was, are you building that, and is someone aesthetically running wires and making cuts and holes and all of that good stuff?
Yes. and I have a story that goes with that, which is, I think, that speaks to a lot of people ask, what's the value of like an artist in residence program, and what's the value of having art around you? And one of those that I can speak directly to in this story, and to answer your question, is the inspiration that it gives the people who are working on those machines. And once they saw this beautiful canvas being wrapped around one of those quantum computers, they looked at all the wires that they were about to put up, and they went and bought colored wires to do them functionally, and organized all of the function of the wires that came in. So a couple of those shots you saw where one of the scientists is working, and they're working down here, but there's all of these wires that are coming up and above, and all of those have been color-coded by function. And that was because of that person saw, wow, you guys really care. Well, I probably ought to care.
Mine is more commentary. So I just wanted to say, if I see this correctly, we're looking at someone who is self-employed and finds the magic in what he does, Jeff, and someone who works for someone else, and it's very heartening to see that you're so connected to what you do that the overtime you spend to do the art part of it in that is inspiring.
Thank you for that observation.
I have a question for both of you, but I'll direct it first at Erik. So as a quantum scientist who has an artist practice, all art, as we know, is generative. So tonight we've been talking a lot about how it's generative formally, how you're improving your technology as a photographer, you're thinking through time and how long it takes to get the photograph and these things. But there's another level of the generative, right? So the question I've been wanting to ask you, not just here, but in other times we've talked, how has the activity of making art, working with an artist in residence, has that opened up a set of questions for the quantum computer or the design of the computer in any way? Has in that process of being creative, working through these images, looking at these images, seeing things in these ways, has that opened up all kinds of a myriad of generative questions about the quantum itself?
That's a great question. I think it's one that I think I would be fun to ask all the folks on the team, because at this point, it's not just me that is building these machines, right? This is a big team of people. And the interactions that we have, the more that those are tighter interactions, the more that they are shared language, the more that you have a common way of describing things and showing one another what is the latest thing that we've designed, then you have this tighter feedback loop, and it's going to enhance the culture, and it's going to help design a quantum computer. As those teams are separated or siloed, and they don't have those kinds of common languages, you would imagine that it's just going to be a lot harder to put those things together. It's a great question, though. You got enough? Yeah. We're on brand here.
So I have a question for Mr. Lovelace. And so I've been told by my 8th grade teacher, science teacher, that all the colors that we see in space from the pictures are actually radiation, and that scientists transform into light and everything, but I want to know your perspective on it. Do you have some type of computer that maybe changes the color of radiation into something we can see, or are these real colors that actually show up on cameras?
The answer is yes. Both are true. I operate strictly in the optical frequency range, the optical light wave, or wavelength range. Images that you see coming from the James Webb telescope, those are shot in the infrared, so those are not real colors as far as what we would see. The idea with that is that you would assign different gases different colors just so you can see the different structures that are going on in these nebulae. because I'm operating in the visible spectrum, now, I do have to say that I use a lot of filters, and the reason for that is my camera on all of my telescopes is monochrome. I do not shoot in color because monochrome cameras are way more efficient. So instead, if I'm shooting a galaxy, which is a red, green, blue target, I will shoot a bunch of images with a red filter, then a bunch with a green filter, then a bunch with a blue filter. I combine them, color correct them, and you have the true colors. So that's how that works. And it saves a lot of exposure time. But I also have filters for one for hydrogen gas, and one for nitrogen gas, and one for oxygen. And these are all the ionized versions of these gases. And I actually have two for hydrogen because it will resonate at two different frequencies, hydrogen alpha and hydrogen beta. And then, I've got a couple of others. But each one of them, the cameras I use will only respond to things generally in the human optical spectrum. They'll go a little bit into the infrared, they'll go a little bit into the ultraviolet, but generally the colors that I do are mostly true. Hydrogen is a very deep red, and nitrogen and sulfur are very deep reds. Oxygen is sort of a teal. So those are the main colors. Sometimes, to give it a little extra beauty, there was one image that I said looked very painterly with lots of golds. That's one where I shifted some of the red filters into the yellow spectrum, and it created these nice gold tones. And it created a beautiful image. And it also helped you see the differences between the different gases and the structure of this. So for my work, it's a little bit of both. But when you're dealing with the James Webb Space Telescope, it's entirely fictitious colors, but informative nonetheless. Color-coded, yes.
All right, we're going to have time for one last question, and then we will all ask all of our questions out at the reception.
Thank you. First of all, it's amazing that you two are brought together for this talk because, one, Jeff, you're on the biggest of bigs, and I'm always interested to ask people, just my friends, if they're more interested in the big, the whole universe, everything, how big it gets, versus the small, because they're both equally as interesting and fascinating, but everyone kind of falls to one end of the spectrum. So this is an amazing duality of the two. So that's so cool that you guys are both together at this talk. But I have a quick question for you, Jeff, first, and then one for Erik after. With the filters that are on all of the telescopes that you have control of, are they automatically applied? Like, is there a robot that switches the filter, or is that a person that that is putting the filter in?
No, that's one of the things that I program into it.
Okay.
I will say take 20 images, 20-minute images with the red filter, and then after that do 20-minute images with the blue filter. So this is part of my programming every afternoon.
Okay, very cool. Wow. And then, okay, so for Erik, working at like the absolute cutting edge of technology that humans have ever created, what is your perspective on, like, with quantum computing in the near future? What do you think, or actually, no, I'll say, do you think that quantum computing will enable us to kind of like have a full understanding of the world? Like, that's kind of subjective, but like we don't know so much right now. So like, do you think it's possible to achieve like pretty much like, okay, we know what's going on?
Question. I would say that the way that I think about, I'll take it to this more existential kind of moment where I think that we've got a lot of work to do as a species to take care of this planet here so that we can continue to live here. And I like to, have kind of the best tools available to do that, to help us. And I believe that a quantum computer could help with that.
So I can't thank Sylvia, Jeff, and Erik enough for, I think, what was just a fantastic evening. I also want to just take a moment to thank all of you for coming and supporting VADA here tonight and VADA Talks. We're so excited to put these together, and it wouldn't happen if we didn't get a great audience turnout, fantastic questions, and it just has fostered such wonderful assemblies of thinkers in our community. So VADA Talks is about bringing together creatives in the Santa Barbara community. And we found it just such a wonderful sort of resource here of people interested and willing to come and speak in this way. Could I have the clicker real quick? You got it? Yeah, okay. All right. So 3 very quick requests. Number 1, we have a survey. So it's on the card that you're probably all sitting on. Please, we take your input very seriously. So it would be wonderful if you could take time. It doesn't have to be the second, but in the next day or two, fill that out. And before turning over the mic to Daniel to kind of wrap us up, I will, as the president of Friends of VADA, make my pitch here. Everything you're seeing here is basically volunteer. So yes, the teachers, work here during the day. We all have our day jobs. But we put this on because of our love. We love the staff here. We love the program. We love what it's doing to the students. And this building is just a building. But what happens in this building day to day is just fantastic. What we see here tonight is great. And if you look down, or as you were here earlier today, there's an aging building that we are going to revitalize. And so anything helps. Helping us completely remodel that building is where we're headed in the next few years. And last, I'll give a plug for the upcoming VADA Talk in October. So we are going to have a debate stage. I won't reveal, but we have a couple of the debaters here in our audience tonight. So it's going to be one heck of a VADA Talks. Daniel, you want to close this?
Hold on. There we go. Thank you. Thanks, Tammy. Thank you all for coming tonight. I mean, wow. Thank you, Erik. Thank you, Jeff. And thank you, Sylvia, for, I feel like I've traveled 1 billion miles together. And I mean, my mind, all of our minds, it's like the philosophical, the aesthetic, the spiritual, the transcendent, the scientific, the intellect. It's unbelievable. It's such a rich conversation. I hope we can continue it outside. I would love to meet you and talk to you. You'll see other students in the crowd. So let's go out and talk together and continue the conversation that we just started right now. Thank you for coming. Okay, we'll see you outside.